The deep ocean has rivers that don't flow in water. They flow as water, dense, dirty, fast-moving water that behaves like a liquid landslide. And here's the shocking, true part right from the start. One of the most famous deep-sea river events, triggered in 1929, snapped multiple transatlantic seafloor cables one after another, letting scientists calculate that the flow raced downslope at roughly highway speeds. It wasn't a wave you could see. It was a fast, bottom-hugging wall of sediment that erased everything in its path. So when you hear that a shipwreck vanished, or that the internet cable on the seabed mysteriously failed, or that the seafloor looks completely different than it did a year ago, this is one of the most real, most underappreciated answers: turbidity currents. And if you're not paying attention to them, you're missing how the ocean actually moves the ground beneath itself. We're going down to about 2,800 meters, the kind of depth where sunlight has been gone for miles. The water is cold, the pressure is crushing, and the seafloor isn't a static floor at all. It's a landscape of slopes, canyons, and channels, some of them carved by events that happen in total darkness, with forces strong enough to bury wrecks and break steel-reinforced cables. Today, we're answering the questions that sound like clickbait, except they're documented ocean science. How can an underwater river even exist when everything is already underwater? What exactly is a turbidity current, and how fast can it really go? What triggers them? Earthquakes, storms, floods, or something even sneakier? How can they reshape the seafloor like a bulldozer? And why can a wreck be there one decade and gone the next? Let's drop, close your eyes, and imagine the descent. At the surface, the ocean looks like a flat, calm sheet. It's easy to believe the deep is just more water. But as you descend, your brain starts losing reference points. Color fades, then even blue disappears. The world becomes a cone of light from a robot, an ROV cutting into blackness like headlights in fog. Down at abyssal depths, you finally see the seabed, pale sediment, scattered rocks, slow-moving life. And it looks still. It looks like nothing dramatic could ever happen here. That's the trick, because the deep ocean's most violent events often don't look like violence. They don't make a crash you can hear. They don't throw a spray into the air. They move like a shadow. And one of the biggest shadows the deep ocean casts is a turbidity current. Here's the simplest, real definition. A turbidity current is a rapid, downhill flow driven by increased density because the water is loaded with sediment, mud, sand, silt, debris, so it hugs the bottom and runs downslope under gravity. That's the key: density. Normal seawater is normal, but mix enough sediment into it and you create a heavier fluid, and heavy fluids want to sink and spread, just like cold air sliding under warm air or a muddy flood rushing down a valley. So yes, it's an underwater river in the sense that it's a channelized flow that can carve pathways, cut canyons, and deposit huge fan-shaped sediment bodies at depth. But it's also more than a river. It's closer to an avalanche, except the avalanche is made of water and sand. Now let's kill the biggest misunderstanding before it grows. A turbidity current is not just cloudy water drifting by. People picture it like a slow brown fog. Some can be slow and gentle, sure, but the dangerous ones, the ones that bury wrecks and break cables, are not gentle. They're not a haze. They're a moving mass that can include a fast front, a thick body, and a turbulent tail. They can surge, pulse, accelerate, and then keep going far longer than you'd expect. And they don't just move through the water. In some cases, they can also involve movement of the seafloor sediment itself, like the ground liquefying and sliding. USGS has highlighted results from large monitoring efforts showing turbidity currents can involve big-scale seafloor sediment motion, not only a dirty current above it. That detail matters for wrecks. Because if the ground under a wreck starts moving, the wreck isn't just getting dusted. It can be undermined, tilted, half-swallowed, broken, dragged, or completely entombed. So where do these rivers happen? not randomly across the abyss. They concentrate where gravity and sediment have a reason to cooperate. Continental slopes, steeper terrain, lots of loose sediment. Submarine canyons, deep channels cut into the margin like river valleys underwater. Canyon mouths and deep-sea fans, where flows spread and deposit. Think of the seafloor like a giant tilted table. If you spill a thick slurry at the top, it will find the low spots, follow channels, and race downhill. That's what the ocean can do, except the slurry is created by nature and the table is kilometers wide. Now, what triggers a turbidity current? This is where it gets creepy, because the triggers range from dramatic to almost invisible. 1. Earthquakes. A quake shakes a sediment-loaded slope and destabilizes it. Sediment can fail like a landslide, and part of that failure can transform into a turbidity current. NOAA explicitly lists earthquakes among common causes. 2. Submarine landslides and slope collapses. Even without a quake, slopes can fail when enough sediment builds up. Collapsing material mixes with water, becomes mobile, and flows. 3. Storms and floods. A major storm can pile sediment on the shelf. A river flood can dump massive loads near the coast. Sometimes that sediment can plunge downslope, especially if it becomes denser than seawater, a hyperpycnal flow, or if it destabilizes later. 4. Smaller but persistent disturbances. Internal waves, strong currents, repeated sediment buildup. Sometimes the system is preconditioned, meaning it's already unstable, and a smaller nudge can trigger a big runout. Research syntheses emphasize that major triggers aren't always required once sediment is preconditioned. So the deep ocean can have a disaster-scale event without a Hollywood cause. Sometimes it's just gravity cashing a check that sediment has been writing for years. Now let's talk about speed, because speed is what makes this story feel unreal. Turbidity currents can move at meters per second. That's not ocean current speed. That's serious moving object speed. A scientific overview of cable break records notes turbidity currents and other sediment density flows traveling from about 3 up to tilde 19 ms and traveling for hundreds of kilometers. 19 meters per second is about 68 km/h, roughly highway speed. And yes, in a famous historical event, estimates derived from sequential cable breaks produced speeds in that ballpark. Now pause for 1 second and picture what that means in darkness. A wall of muddy water hugging the seafloor, moving at highway speed in a canyon that can be hundreds of meters deep. You wouldn't see it coming. If you're a cable on the bottom, you just get hit. If you're a wreck sitting in a channel, you just get buried. And that leads directly to the most famous real-world proof that these events can be fast and destructive: submarine cables. If you want the most brutal, accidental measuring device humans have ever installed on the seafloor, it's the global network of undersea telecom cables. Because when turbidity currents cross them, they can break them. And when multiple cables break one after another, you can time the failures and infer how the flow moved downslope. One classic case involved a 1929 earthquake off Newfoundland, Grand Banks, that triggered submarine slope failure and a turbidity current. Multiple cables broke in sequence, and later analyses and summaries discuss high flow speeds derived from those breaks. This isn't folklore. It's one of the clearest demonstrations that these deep-sea events are real, large, and capable of traveling huge distances. Now bring that back to the title. Underwater rivers can bury ships. Why wrecks vanish? Because wrecks don't always sink into a safe, stable, museum-like environment. Sometimes they sink into a landscape that is actively being resculpted. There are 2 major ways turbidity currents make wrecks disappear. A. Burial. A turbidity current carries a massive load of sediment. As it slows, it deposits that sediment. If a wreck is in the deposition zone, it can be blanketed, meters of mud and sand settling over it. If you come back later with a camera or sonar, you may see nothing but smooth sediment. And that's a key psychological trap. People imagine the seafloor as bare rock. But huge areas are soft sediment plains. A wreck can be buried like a car left in a desert during a sandstorm, except the sandstorm is a liquid avalanche. B. Reshaping and transport. If the flow scours around the wreck, it can undermine it. Think of a flood on land eroding the soil under a bridge pier. The bridge can collapse, not because it was pushed from above, but because it lost support underneath. The same logic applies underwater. A wreck gets undercut, parts collapse, pieces slide downslope. The wreck becomes scattered debris instead of a recognizable shape. And when debris scatters across a wide area, it becomes much harder to identify. Now let's be honest about something. People often imagine a turbidity current hits the wreck and carries it away like a raft. Sometimes parts can be moved, yes, but the more common reason wrecks vanish is simpler and more brutal. They get buried and the seafloor gets smoothed over them. Sonar sees shapes and contrasts. Burial removes contrast. A wreck-shaped silhouette becomes a flat sediment blanket. It's not magic. It's geology happening faster than you think. Okay, so if these things are so powerful, why don't we talk about them more? Because they're hard to witness. They happen in darkness, far offshore, unpredictably, and often too fast for a casual observation. Also, they're dangerous for expensive instruments. To study a turbidity current, you often have to place sensors directly in a canyon and hope a flow occurs while the instruments survive. And that's why one of the most important modern efforts to understand them has been direct monitoring, especially in places like Monterey Canyon, where researchers have instrumented the canyon and observed repeated events. MBARI's Coordinated Canyon Experiment describes multi-year monitoring of sediment gravity flows, emphasizing that turbidity currents can destroy underwater cables and infrastructure, and that they are difficult to study, exactly because of their unpredictability and power. And peer-reviewed work based on time-lapse seafloor surveys has measured front speeds in canyon systems, showing that these are not hypothetical forces. They are measurable, moving events that reshape the bottom. So in the past, we inferred turbidity currents from deposits and cable breaks. Now, in some places, we can actually watch the seafloor change and record the flows. That's a big deal, because it means we're finally seeing the mechanism, not just the aftermath. Let's zoom into the anatomy of one of these underwater rivers, because the mechanics are what make it believable. A powerful turbidity current often has a front, the leading edge where it first hits you, a body thicker, carrying the main sediment load, a tail more diluted, trailing turbulence. The flow is turbulent, and that turbulence helps keep sediment suspended, like a perpetual sandstorm inside a liquid. And here's the feedback loop that makes them scary. As the flow moves, it can erode the seabed, picking up more sediment. More sediment means the flow becomes denser. Denser means it hugs the bottom more strongly. That can increase its ability to keep moving. So the flow can feed itself on the seafloor, not forever, but long enough to travel astonishing distances. This is one of the reasons turbidity currents can carve submarine canyons over time and create deep-sea fans by repeated deposition. Britannica describes dense slurry flows moving down canyons and depositing sands in deep water, building submarine fans and leaving turbidites. That's the long-term view. But your video is about the short-term shock. The seafloor can change fast. Now, let's talk about bury ships in a way that feels real, not sensational. When people hear that phrase, they imagine a ship sinking and instantly being swallowed like quicksand. That's not how it usually works. What happens is more like this. A ship sinks and lands on a sedimented seabed. For years, it might sit there, slow corrosion, small sediment drifts, scavengers. Then one day, maybe after a quake, maybe after an unusual storm season, an event triggers a turbidity current upstream in a canyon. The flow travels downslope, hugging the bottom. If the wreck is in its path, the wreck experiences a sudden increase in current, zero visibility as sediment clouds the water, possible scouring at the base, and then deposition, sediment settling out in thick layers. After the flow passes, the wreck may be partially buried, deeply buried, damaged and scattered, or located under a smooth new skin of seabed. So the wreck didn't teleport, it got repainted over. Now here's a terrifying thought that's also true. The deep ocean doesn't need to destroy something to erase it from our awareness. It only needs to hide it from our sensors. A wreck can be intact but buried. A cable can be intact but covered. A whole debris field can be smoothed into a subtle hump that looks like ordinary sediment. And because deep-sea surveying is expensive and intermittent, changes can happen between visits without anyone watching it happen. That's why the deep feels mysterious. Not because it's supernatural, because it's hard to monitor. Let's bring this to 2,800 meters specifically. Why that depth? Because that's right in the realm where submarine canyon systems can connect to deeper channels and fans that spread across the abyssal plain. Many continental margins descend through depths like this, and by the time a turbidity current runs out, it may be moving through deep channels or depositing across fan systems at abyssal depths. In other words, 2,800 meters is the neighborhood where the river can be fully developed, deep, powerful, and far from the triggering shoreline. It's where the deep sea receives the continent's sediment deliveries, and it's where a wreck can become collateral damage. Now let's do the cinematic version, without making anything up. Imagine your ROV hovering above a wreck site on a deep seafloor channel. You see a shape, ribs of metal, a collapsed deck, a shadow. The sediment around it is smooth, like dust. Your lights show marine snow drifting down, slow, constant. Everything feels still. Then hours later or days later, your sensors in the canyon upstream detect something. The current meter jumps, pressure changes, seafloor instruments register movement, and then the camera feed changes. The water turns hazy, then brown, then opaque. Visibility goes to zero. The ROV lights become useless. You're inside a moving sandstorm. The flow lasts minutes, maybe longer. Then slowly it thins. The water clears. And when you go back to the wreck location, you realize you're looking at a different world. The wreck outline is softer. Parts are gone. Or the wreck is completely covered and the site is flat. That's a wreck vanishing. Not a mystery, a process. Now, one of the reasons turbidity currents are so important is that they don't just move wrecks and break cables. They're one of the planet's major sediment transport systems. They move sand and mud from continental shelves into the deep ocean. They build deep-sea fans that can be enormous. They create layered deposits, turbidites, that geologists read like pages of history. Those deposits often show a classic pattern: coarser material at the bottom, fining upward as the flow wanes, one of the fingerprints of a turbidity current deposit. So the same force that buries a wreck is also one of the forces that builds the deep seafloor itself. The abyss is not just sitting there. It's being constructed, layer by layer, by events like this. Now let's talk about cables again, because it's the most modern "why should I care" connection. Undersea telecom cables carry the vast majority of international data traffic. Papers and reviews on cable hazards emphasize that turbidity currents are a major geohazard for this infrastructure. And the ocean doesn't care that the cable is expensive. If a turbidity current hits it, a few things can happen. The flow's force can physically snap the cable. The flow can drag the cable, creating tension until it fails. The flow can bury the cable, altering local stresses. Associated slope failures can break the seabed and rupture the line. So when people think internet outage, they imagine servers and hackers and satellites. Sometimes it's literally mud avalanche in a deep canyon. And that realization is exactly the vibe of your channel. The real world is stranger than our assumptions. Now, you might be wondering, If turbidity currents can be so fast, how can anything survive them? Some things do, especially if they're not in the main path. But for seafloor animals living in channels, these events can be ecological disasters and also ecological opportunities. A turbidity current can bury habitats, smother filter feeders, strip away sediment and expose fresh surfaces, deliver organic material from shallow waters into the deep, so they can reset ecosystems, disturbance followed by recolonization. In some ways, they're like underwater wildfires, destructive locally but part of a larger natural cycle in some regions. How do scientists catch them in the act? A few main ways. 1. Instrumented moorings and seafloor landers. Current meters, pressure sensors, turbidity sensors placed along a canyon. 2. Repeat bathymetry. Map the seafloor, then map it again later. Compare the changes. The AGU paper on time-lapse seafloor surveys shows how repeated mapping reveals erosion and deposition caused by turbidity currents and measures front speeds at different canyon positions. 3. Sediment cores. Drill into the seabed and read the layers. Turbidites act like timestamps. 4. The accidental method. Cable breaks. If multiple cables fail in sequence, the timing can constrain the flow's progression, famously used in the Grand Banks case and discussed in geohazard literature. 5. Long-term canyon experiments. MBARI's Coordinated Canyon Experiment is a major example of coordinated monitoring aimed at understanding how these flows start, evolve, and impact seafloor infrastructure. The theme is consistent. These flows are hard to capture because they don't schedule themselves. So when we do capture them, the data is gold. Now let's land the title emotionally. Why wrecks vanish? Because humans want permanence. We want the ocean to be a stable archive. We picture wrecks like museum exhibits. Once they sink, they stay put. But the deep ocean is not a museum. It's a dynamic sediment system. A wreck is just an object on an active surface. If that surface is part of a canyon highway, the wreck is living on borrowed stillness. And turbidity currents are the moments when the ocean cashes that debt. So if you ever hear someone say, they found the wreck, and then later they couldn't find it again, don't jump straight to myths. Ask the boring, terrifying questions. Is it near a submarine canyon? Is it on a continental slope? Is it in an area with known sediment transport? Has the region had earthquakes, major storms, or flood events that could destabilize sediment? Because sometimes the answer is brutally simple. The seafloor moved. Not by an inch, by meters, and it moved like a river. If you enjoyed this kind of deep ocean reality, real phenomena that sound impossible until you understand the physics, hit like and subscribe, because this Abyss series is going deeper, one true anomaly at a time. And next time, we can connect this episode to something even stranger, places where the seafloor has lakes of brine that trap animals at the shoreline, or the false seafloor of living creatures that rises at night and fools sonar. But for now, remember this. In the deep ocean, history isn't only lost to rust. Sometimes it's lost to moving mud, an underwater river that can erase a wreck without breaking a single piece of metal. It doesn't need monsters, it just needs gravity.